Alrighty, lads and ladies, welcome back to Calc 1 Honors. Today is a good day because today we're going to go a little bit further into solving area and distance problems. We're going to talk more 5.1 stuff. So last week, of course, we introduced this concept of finding an area under a curve. And today we're going to push further forwards with that with a couple more examples where we're finding the exact area under a curve using that whole gnarly Riemann sum limit thing. But then I'm also going to introduce some new notation, and I'm going to show you how to apply some of these things to physics problems. Warning, I'm not a physicist. There may be other ways to think about this stuff, but I'll present to you what I believe to be the clearest and simplest way to think of it from a mathematics perspective. So, with that said, let me flip on the document camera and we can get started. All right. I know everybody's anxious to get their tests back. I am working on them, but they are not ready yet. I'll do my best to have them ready for you by Wednesday. Dealing with a cheating scandal again in my algebra classes, so hopefully that won't consume too much at this time. But thankfully, I trust you guys to have been above board. All right, so this is MAC 2311, Calc 1 Honors. And today is the 8th of November, 2021. And I do have a little update for you guys regarding Calc 2 Honors, those of you who are interested. The honors version of Calc 2 is still running in the spring, still being taught by me, still being taught in person on campus, but the time may change. So I noticed last week a scheduling conflict. I am scheduled to teach one class like this, an online class at 11 a.m. and I was scheduled to teach Calc 2 Honors in person on campus from 9:30 to 10:45. It is physically impossible for me to finish teaching a class at 10:45 on campus and then get home by 11 a.m. and start a virtual class here. So a quick little announcement or note. Calc 2 Honors. Hopefully, I sent the email out to my chair and she's talking with Bonnie. Hopefully, Bobby will be moving to Monday, Wednesday, Friday at 8 a.m. 1 hour, little over an hour earlier than it was originally planned to be. They may end up doing something else with it. They may shove it to a different time slot, but that was the one that made the most sense. So just a heads up, if you and I had talked about that, I probably told you that it was Monday, Wednesday, Friday at 9:30. That is certainly not possible. And because the other class, the Calc 2 class right after that, a virtual class at 11 a.m. already had a bunch of people registered, I don't think they're going to let me move that one. So the hopeful solution here is to move that honors class an hour earlier to 8 a.m. All righty. So today we're going to do more 5.1 on areas and distances. And we might introduce 5.2, which is on the definite integral. So what I would like to start by doing is just popping open your textbook and taking a quick peek. So the Calc 2 Honors class is going to run in person on campus. That is the plan. One other possible solution would be to moving the Calc 2 to a virtual class, like a sync class online like this one. But I am getting pretty tired of teaching online classes. I really miss teaching in person. So when they told me I could do it in person, I asked for that. But we'll have to see what they come up with. If Bobby says moving it to 8 a.m. is going to kill registration because nobody's going to sign up for an 8 a.m. class, then we may have to start looking into alternatives. And one of those alternatives might be running it online. But we'll see. I could also teach it out of a high flex room, which would mean you guys could zoom in if you wanted, or you could come in person if you wanted. It'll depend on kind of what Bobby says, because he gets the last say as the head of honors. So last time we worked through a bunch of examples like these, we saw how mo rectangles equals mo beta. We talked a little bit about overestimates and underestimates. There is a different way of thinking about these things where you take your sample points to come from anywhere in those subintervals. This leads to other concepts like upper and lower sums. I'm not going to beat you guys up with that stuff. It's nasty and nobody actually uses it for computation purposes. What we can do, let's see. Yeah, let's talk a little bit about distance. So they don't actually introduce the notation here, right? Yeah, no. Okay. So we will be getting into 5.2 today. And the only thing I want to talk about a little bit before then, we'll talk a bit about overestimates and underestimates, and then we're going to talk about this distance thing. So recall, given a function f and an interval AB, can approximate the area under the graph y equals f of x from x equals a to x equals b as either the left endpoint Riemann sum, which is the sum from n equals, using I equals 0 to n minus 1 f of xi times delta x, or Rn, which is the sum from I equals 1 to n of f of xi times delta x, where in either case, delta x is b minus a over n. It's sort of the width of each rectangle. And the sample points xi, the endpoints of those subintervals, are a plus I times delta x. So to run one of these computations, the first thing you do is find delta x. Then you calculate your xi's. Then you plug all that stuff into either one of these formulas, whichever one you want to use. Generally, we use this if we're going to take a limit and go for the exact value. If you're trying to approximate, you may find the left and right sum separately. But I wanted to say here, it's a little note. If f is increasing on the interval AB, something like this. Maybe here's A, here's B. And you chop this up into some pieces and you look at those rectangles. I'm sorry, I'm missing my blue pen today. Then the left sum will be an under.
Could you see that came up slightly?
Oh, yeah, sure, sorry.
Oh, thank you.
So if my function is increasing, then all the rectangles that come from the left endpoints will be a bit too small. And the area I get will be an underestimate. So if f is increasing, then ln is an underestimate. I'll do my best to reproduce this picture over here. So drawing in Rn. Here's A, here's B. I'll chop it up. More things, guys. And Rn will be an overestimate. So specifically here I've drawn L5 and R5, but it doesn't matter what N is. So if your function is increasing on the interval AB, or at least on the open interval, so the link is always posted to the Canvas announcements. I don't send them out through emails. If you didn't get something, then maybe it's the case that you're not getting the emails from your Canvas announcements. I'm not sure. But yeah, if you're ever looking for the link will always show up here in the announcements. That's where I drop it each morning. Same place you go to review the videos. Okay, so similarly, right, if f is increasing, then ln underestimates and rn overestimates. Similarly, if f is decreasing, then ln will overestimate. And Rn will underestimate. These are things that you can see right away when you draw the picture, but they're also just good things to know. So if you're looking at an increasing function, then the left endpoints, well, that means that the function is always smaller at the left endpoint than at the right endpoint. That's what it means to be increasing, going up as we go left to right. So the ln's would be an underestimate. And similarly, if you're going up from left to right, then that right endpoint is the tallest the function is anywhere on that subinterval, which means that rectangle will poke out over, so Rn is an overestimate. If you change this to decreasing, then the left endpoint is the tallest endpoint on the subinterval, which means ln will overestimate. And the right endpoint is the lowest endpoint on each subinterval, which means Rn will underestimate. And these are just good facts to know because they can save you time. Also a good source of true-false questions. Okay.
Will subtracting the underestimate from the overestimate give you a difference, like a proper one, if you use like the same amount of rectangles and everything?
It's a good question. So if suppose you have an increasing function f on the interval AB and you subtract Rn minus ln, right? You take the left estimate and you subtract it from the upper estimate. It's not going to give you an accurate representation of the area. What that would do is give you double the error, right? So if you take this, which is the purple area rectangles here, and you subtract this from it, what you're going to get is the amount that each rectangle here pokes over, plus the amount that each rectangle here misses under. But there is something like that. Remember last time, if we average ln and rn, we get a better estimate than either of them. And there's a name for this thing. This thing is called Tn. And the reason for that name is that when you average the areas of two rectangles, what you get is the area of the trapezoid formed. Here. Yep, yielding Tn, which is the average or 1/2 of ln plus Rn, which is so named because it's called the trapezoid rule or trapezoidal approximation. And I'll draw the picture here that goes with that. Try to draw this nice and big because we need plenty of space to see what's going on. And let me say like 1, 2, something like that. What we would be looking at here then is, I think, kind of what we intuitively want when we talk about combining or taking differences of ln and rn. Instead of a rectangle, you're approximating each piece there by a straight line. And this is actually a really good approximation for most functions. You remember we used this on Friday of last week to try and get the area underneath x squared from 0 to 1. So like the left endpoint approximation for x squared from 0 to 1 gave us like 0.2 something. The right endpoint approximation for x squared from 0 to 1 gave us like 0.4 something. The exact area there was 1/3, which is 0.33333. And the trapezoidal approximation, which is what you get by averaging the left and right endpoint approximations, was like 0.3 something. It was very, very close. So sort of the best thing we can do to combine ln and rn to get a better approximation is to average them. And it's nice because it doesn't require doing any fresh calculation beyond like adding these and multiplying by 1/2. There are other ways to improve this. So we talked about using more rectangles. We talked about averaging these two. The thing your book does, which I am actually not a fan of because it's a sloppy computation, are midpoint approximations. So here you've got 1, 2, 3, 4 rectangles. But notice that the height of each isn't coming from the left endpoint or from the right endpoint. It's coming from the value of the function right at the midpoint of each subinterval. This midpoint thing is different from Tn, right? The geometry is different and the formulas are different. Your sample points there have to be calculated as the midpoints of each of those subintervals. So like your subintervals, if you're going from 0 to 2 with 4 rectangles, would be at 1/2, 1, 1.5, and 2. So the midpoints of those would be at 1/4, 3/4, 1 1/4, and 1 3/4. And then you'd plug those in and do your calculations. It's a little bit nasty, and it's not something that is easy to like use bigger and bigger values for n because you have to recalculate the midpoints every time you increase n. It's just not a pleasant scheme. But that's one other way you can try to improve things. But for my money, the things that are worth doing, left and right approximations are easy, right? It's just a matter of changing the sum to go from 1 to n or from 0 to n-1. And then the trapezoidal approximation, this is almost always going to be better than the midpoint approximation. And it's even easier to calculate because if you've got ln and rn already, you just add them up and divide by 2. Super duper easy. There are other tools for this. And you'll learn a bit about this in Calc 2. Simpson's rule. which is another way of approximating the area under a curve, kind of has to do with finding a quadratic function that does a reasonable job of approximating the blue curve here, and then using some sneaky, show you here. Yeah, so using some kind of sneaky geometry to get the areas of each of those little pieces. And this is the only thing that I could possibly show you that is an improvement on the trapezoid rule. But it's not something that we talk about in Calc 1. You talk about Simpson's rule a little bit in section 7.9 in Calc 2 if you're unlucky and you get a professor who likes numerical analysis. I don't even bother with it there. But if you are the sort of person who's going to be using computers to calculate areas under curves, the Simpson's rule is a powerful tool. It is more powerful than the trapezoid rule. And you see here they talk about constructing Simpson's rule by taking both the midpoint and trapezoid rules and combining them. I'm not going to beat you up with that. The most complicated thing I'll ask you to do is a trapezoidal approximation, which you find by averaging the left and right Riemann sums. Really, none of this is all that important. I hate to say it like that, but it's true. Because the big deal, way more important than any approximation, is the actual fact. So we had a discovery last time. If A is the exact area under y equals f of x from x equals a to x equals b, then a can be thought of as the limit as n goes to infinity of Rn, or the limit as n goes to infinity of Ln. And both of these are the same as the limit as n goes to infinity of Tn. All of these will give you the exact area if you send n to infinity. And usually we use the limit as n goes to infinity of Rn, because it's just the nicest one to work with. The kind of pieces are the least ugly there. Now we did use this last time to calculate the area under x squared from 0 to 1. I would like to use this to calculate a few more areas, and then we're going to talk about applications to physics. Let me remind you of some summation formulas. We need these. There was one that I didn't share with you last time, and I apologize for that. The sum from I equals 1 to n of 1, that's just n. And then the other ones we did have, the sum from I equals 1 to n of I is n times n plus 1 over 2. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And the sum from I equals 1 to n of I cubed is the square of n times n plus 1 over 2. And then the other thing that I want to talk about while we're revisiting the summation operator is that if you have a sum from I equals 1 to n of some constant times, some, how do we write this? You guys don't have the notation. I'm just going to write it AI. This would be k times the sum from I equals 1 to n of AI. So the AI here could be anything. It's just some function of I. That's the idea, just some stuff that has i's in it. So if you've got a constant multiplying inside your sum, that constant can be popped out. And if you have a sum or a difference of terms inside here, both of which depend on I, you can split that sum up. Into two separate sums. These two things on the right-hand side here tell you that the sum operator, capital sigma, is a linear operator. And you may remember way back when we talked about the derivative for the first time, we said that ddx, the differential operator, is also a linear operator. Linear operators are nice. They're our favorite operators. So with this in mind, I just want to grab a problem from your textbook. Let's find an exact area. Expression for the area, you did plenty of that last time. Do we have a problem? Nah, not really, man, not many. Boy. Yeah. No. Yeah, pretty much all estimates, right? Bummer. Let me find the exact area. I'll just make one up. Let's find the exact area under f of x equals x plus x cubed from, we'll do 0 to 1 again. Let's go from 0 to 2. Why not? We'll give ourselves a challenge. Now, real quick, what does x plus x cubed look like? That is a cubic with roots at 0 and -1. Here he is. Oh, did I say x? Yeah, okay, that works. Yeah, sorry, no root at -1, just root at 0. So we're looking for this guy. Here, we're looking for this area. And of course, the boundary is curvy, so it's hard. So we need our Riemann sums. Yeah, sure. Sorry, I can flip back here and get the summation rules down. So these I gave you last time. This is one that is kind of silly, right? It's just 1 plus itself n times. Of course, that's m. But when you're staring at a bunch of things that look like this, sometimes it's, even though thinking about this on its own is like obvious, it's one of those things that in context, I think it's nice to have the formula for. And then the rules on the right over here just say that you can pop constants out of the sum. So if you have a sum of a constant times some stuff, you can pop that constant out here. And this one says if you have a sum with a sum or difference of two things inside, you can split that up into the sum of the first thing plus or minus whatever you had in here, the sum of the second thing. Cool. Yeah, no problem. Okay, so let's do it. Let's try to find that area. Remember what we need here, we need the limit of the Rn's. And Rn is sum I from 1 to n, f of xi times delta x. So we want this, and we need a, which is the limit as n goes to infinity of Rn. So what we're going to do is we're going to build up this sum, the right endpoint Riemann sum with n rectangles. We're going to try to simplify this as much as possible, maybe splitting it up into multiple pieces. And then once we've simplified it, we'll apply our summation formulas to write it as a nice algebraic function of n. And then we'll take the limit as n goes to infinity. So I'm going to start by cooking up Rn. Remember, you always begin with delta x. So delta x is always b minus a over n. Here, I don't have a fixed number of rectangles. I need to leave n as n because I'm going to send n to infinity. But a and b are numbers. This is 2 minus 0 over n, which is just 2 over n. And the xi are always a plus I times delta x. So that's 0 plus I times 2 over n, which is just, I'll write it as 2I over n. So that means my Rn is sigma I from 1 to n f of xi, which is 2I over n, times delta x, which is 2 over n. And the function f here is f of x equals x plus x cubed. So that means I need to take 2I over n and plug it into f. So this is going to be sigma I from 1 to n. F of 2I over n is 2I over n plus 2I over n all cubed. And then we still have our 2 over n from delta x. And you see what I mean? These sums can get a little bit gnarly. You certainly saw that in your homework. The only ones we could hope to even calculate exactly using the formulas we have are polynomials. And even then, we need the degree to be less than 3 because I cubed is the largest sum that we have a nice formula for. Although there are formulas for larger powers. They come out in terms of Bernoulli numbers. So the end goal,
I have a question.
Yes.
For the if fx1 is I use I plot x1 into the formula, and if x2 is I plot the x2 in the formula. So this xi it means the Roman sum at f1 plus x2 f1 plus f of x1 plus x multiple x1 fx2 multiple x2 in until fxi multiple xi.
It's true, yep. So this would be 2n over n, which would just be 2. So we can write down the first few values of xi, like x1, x2, x3, and so on, by plugging into this formula. And then we could plug those specific numbers into the function f. But remember what we're going to need to do here. We're going to need to send n to infinity. So when you try to write this sum out in the long form, like f of x1 plus f of x2 plus f of x3 and so on, you're going to inevitably have some ... dots in there, right? Because n is here considered as like a variable rather than a fixed constant. So because at the end here, my goal is to send n to infinity. They didn't say use 5 rectangles or use 10 rectangles. We have to find the formula for n rectangles in general, and then at the end, send n to infinity. So on these problems where they say find the exact area, in those cases, we really do need to continue working with the sigma notation. There are ways to write this out, but it will inevitably require some ... dots. And those don't lend themselves so nicely to applying these summation formulas. So the idea here, the function f of x equals x plus x cubed, one of those pieces, the piece that comes from the x, is going to result in us using this formula. And one of them, the x cubed piece, is going to result in using this formula. And so in order to apply these formulas, I want to continue working in this notation. Now, if you've practiced it another way and you've become comfortable and confident, like writing things out long form, that's okay. Just make sure that however you're getting there, you're getting the correct result and you understand what you're doing. So this, for example here, this summation formula, I could write this as 1 plus 2 plus 3 plus 4 plus ... out to plus n equals n times n plus 1 over 2.
Put the dot cam slightly.
Yeah, so I could write this this second formula here in this form. And so you could write your Riemann sums out in a form like this, as long as you're comfortable applying these results in that notation. But I will always work in the sigma notation because it's just so much less writing.
Thank you.
Of course. Here we go. So the game is going to be to distribute the 2 over n to these two terms, then to split the sum up into two separate sums. So this is sigma I from 1 to n, 2i over n times 2 over n plus 2i over n all cubed times 2 over n. And then I will write this as sigma I from 1 to n. 2i times 2 is 4i, and n times n is n squared, plus 2i cubed is 8i cubed, times 2 is 16i cubed. And then downstairs here I have n cubed times n is n to the 4. So just a little bit of algebra. And then once I get to a nice clean place like this, I'm going to say, okay, now my exact area is the limit as n goes to infinity of this sum. For I over n squared plus 16i cubed over n to the 4. And in order to take this limit, I need to rewrite this sum using my summation formulas. And in order to use those summation formulas, I need like just sigma of I and just sigma of I cubed. So I need to split this sum up into two pieces and bring the constants from each out. So here's what that looks like. That is limit as n goes to infinity.
Thus, if I want to evaluate the equation, I always use limit x approach infinite.
If we want the exact area, then yeah, we'll need to take the limit as n goes to infinity. If you're okay with an approximate area, then you can just use like n equals 4 or 5. But if we want the exact area, we need the limit. So first, I take this sum and I split it up into two sums, the sum of the first piece plus the sum of the second piece. That's that very last rule from the previous page. Then from each of those sums, I pop out anything that doesn't have i's in it. So from the first sum, I can pop out a 4 over n squared. And I'm left with just sigma I from 1 to n of I. And from the second sum, I can pop out 16 over n to the 4. And what's left is the sum from I equals 1 to n of I cubed. Who the hell is this? Sorry, this is a weird number. Hello? Ugh, spam calls. All right.
Was it for your car's extended warranty?
No, this time it was Sarah from Discover.
Oh, okay.
I don't have a Discover card. All right. Often it is the warranty though. Yeah. So the 4 over n squared doesn't have anything to do with the sum because the sum is just over the variable I. So he can come out of the first guy. And the 16 over n to the 4 also doesn't have any i's in it. So he can come out of the sum. And what's left from the second guy is just I cubed. What's left from the first guy is just I. And now this is one of my summation formulas. This is one of my summation formulas. So I have here limit n to infinity 4 over n squared times the sum from I equals 1 to n of I is n times n plus 1 over 2. And then I have here plus 16 over n to the 4 times the sum from I equals 1 to n of I cubed is this thing, but squared. N times n plus 1 over 2 all squared. So this is what we need to take our limit as n goes to infinity of. We'll use our limit laws. I'm going to give the limit to this piece and this piece separately. And then we'll kind of clean each one up algebraically as much as we can until we can figure out how to take that limit. We could use L'Hopital's rule if we wanted. But I think each of these will yield nicely to that renormalization trick. So that's the one I'm going to probably use. But let's see what we get. So lim n to infinity. Each piece gets their own limit. I'll distribute this. This is n times n plus n times 1. That's 4n squared plus 4n. And then downstairs I have n squared times 2 is 2n squared. Plus lim n to infinity. Here I might need to do a little bit more work. Let me see. So this is going to be n squared times n plus 1. I'll write the whole thing. This is 16 times n squared times n plus 1 squared all over. I've got an n to the 4 and 4 squared. That's 4n to the 4. This piece is actually looking pretty Gucci. I can take this limit now if I wanted to, but I'm going to hold off for a second because this piece I need to multiply out the top and do some algebra. First, maybe let's cancel n squared and n to the 4. And in the first piece, let's I'll just leave it alone. Whatever. N to infinity. Well, no, I can factor in canceling n. Let's do that. So this will become 4n plus 4 over 2n. And this piece will be lim n to infinity. 16 over 4, we can also clean that up quite a bit. That's just 4 n squared over n to the 4. Both of the n squareds die, and I'm just left with n plus 1 squared here, and then downstairs n squared left. We're just doing algebra. This is lim n to infinity. I'll leave this one alone for now. It's fine. There is more we could do with it, but it's good enough for now. This piece, n plus 1 squared, is n squared plus 2n plus 1. So this piece is lim n to infinity 4n squared plus 8n plus 4 over n squared. Move that up. There we go. All right. Now each of these, I can take the limit of. You could again use L'Hopital's rule. The top and bottom are both going to infinity. Top and bottom are both going to infinity, but you really don't need to because the algebra has actually become super clean. If I do one more simplification step here, 4n over 2n is 2, and then 4 over 2n is 2 over n. And then I have here plus lim n to infinity. Splitting this up, 4n squared over n squared is 4, plus 8n over n squared is 8 over n, plus 4 over n squared. So I think this is a nice way to take these limits. Here, the 2 over n goes to 0, so you just get 2 plus 0, plus. Here, the 4 chills, 8 over n and 4 over n squared both go to 0. So you get 2 plus 4, which is 6. And that's it. That's the area here. So the exact area under that curve, no approximations, no error, no nothing. The exact area under that curve is 6 units squared, 6 square units. Pretty cool, right? No small amount of work, though. Quite hard. Quite hard in the sense that there's a lot of calculation, a lot of algebra, a lot of work with sigma notation, and the inevitable use of those summation formulas, which are kind of a pain to remember. All right. I am going to tell you how to find the exact area under a curve without doing all of this, without doing any of this, in fact. But before I can do that, I want to introduce a concept from physics that is very important. And that is finding distance traveled from a velocity function. This is something that intuitively kind of everybody knows. If I tell you exactly how fast I'm going and in what direction I'm going at every moment in time over a trip, intuitively, you should be able to reconstruct the trip, right? If I tell you what my velocity is everywhere along my little drive, you should at the very least be able to figure out how far I drove. It turns out to be the same problem as finding the area under the curve. And the reason for that is that your distance is equal to the rate of travel times the time, right? If I'm going 2 miles an hour for 5 hours, then I will go 10 miles. So you can reconstruct from the information of how fast you're going and for how long you went that speed, the distance you traveled. The fun thing is, what if your velocity isn't constant? This works great. If your velocity is constant. Well, what am I doing when I build a Riemann sum? Let's look at a picture. When I draw these rectangles, what am I really doing? I'm pretending like this function is constant over this subinterval. Constant, 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 constant. Every time we approximate the area under a curve with some number of rectangles, I'm pretending like that function is constant on each of the subintervals. Now, of course, that's not true, right? And that's why these are approximations rather than exact values. Yeah, so the blue is the actual curve. And then each one of the tops of these rectangles is a horizontal line. Well, a horizontal line is a constant function. So when I say the area under the curve is approximately the area of these rectangles, what I'm really doing is saying, instead of finding the area under this curve, I'm going to find the area underneath this piecewise constant function that I get from the curve. So what are we going to do to find the distance you travel over a journey where your velocity isn't a constant? You're going to pretend like it's a constant on a bunch of small subintervals. Is that the truth? No, very rarely does anybody go on a journey and have piecewise constant velocity. Usually you accelerate and decelerate in a smooth fashion. But it will serve well enough for an approximation. And if you want exact values, you can go back through the procedure we just did. So let me sketch for you the graph of some velocity function. So this is going to be my t-axis down here. My horizontal axis is the t-axis. And this will be my velocity on the vertical axis. And I'm going to say that my velocity curve looks something like this. Here's the time b, and here's the time a. If you chop this interval up into a few subintervals, let me just do 4 for now, and construct a Riemann sum, say the right endpoint Riemann sum. And you think about what each of these rectangles could represent in the physical situation. So good enough. So let's think about, I'll call the first rectangle's area A1, the second rectangle's area A2, A3, and A4, like we did before. So A1 is all of this area, right? A2 is all of this area, A3, all of this area, and A4, all of this area. And let me call this y value, well, what would it be? This is A is x0, or t0, I guess, if t is my, right, using that same notation, t0, t1, t2, t3, and v here would be t4. The y value there is v of t1, the velocity at time 1. The y value here is v of t2. This y value would be v of t3. And this y value would be v of t4, right? And each of these widths would be delta t, of course. So A1 is v of t1, that's the height, times delta t, that's the width. V of t1, this is a rate. It's a velocity. It's how fast I was going at the time t1. And delta t, this is a time. So that rate times that time, this is a distance. What distance? Well, it's the distance you would travel if you were going exactly this speed, that y value, right? Exactly this speed for exactly this time. So if you're going exactly v of t1 for exactly delta t, then the exact distance you would cover over that time is the area of the rectangle A1. Is that exactly the distance I covered? No, that would be the pencil shaded distance. That would be the pencil shaded area in there. But is it a reasonable approximation? Sure, as reasonable as any of the other approximations we've been doing. So because it is a rate times a time, it is a distance. And what distance? It's the distance you would go, you would travel if your velocity was constantly v of t1 on the first delta t interval. Sorry about the spacing issue there. So what is that distance? It's the exact distance you would travel if your velocity was constantly this velocity, v of t1, the y value here, over this first time interval. So this is the distance you would go traveling v of t1 for delta t seconds. And then this is the distance you would go if you were traveling v of t2 for delta t seconds. This is the exact distance you would go if you're traveling v of t3 for exactly delta t seconds, and so on. And by thinking about the limiting case where we use more and more and more rectangles, you see that the exact distance you travel is the exact area under the velocity curve. I'll move this up just a little bit. Not a tiny bit. Focus. A1 plus A2 plus A3 plus A4. This is approximately the pencil shaded area. And that pencil shaded area is exactly the distance traveled moving according to v of t from time t equals a to t equals b. So each little height is a little speed, is a little rate. It's a velocity. It's the y value on your velocity function. It's your speed. And each little width is a little time interval. And when you multiply a speed times a time, you get a distance, right? Distance is equal to rate times time. And if you use infinitely many rectangles, that shaky equal sign becomes exact. And that gives you the exact pencil shaded area. Therefore, the exact pencil shaded area must be the exact distance traveled if you're moving according to that velocity function from time t equals a to t equals b. Pretty cool, right? There is a little catch here. And those of you who found the velocity problem on exam 1 a bit frustrating might be recognizing the catch already. What assumption am I making about this velocity function in this argument? Hint, I've actually been making about the same assumption about all of these area problems. Very good. We never change direction. In other words, the velocity function is always positive. And you'll notice that every problem we've looked at, all of these area problems, the function we're finding the area bounded by is a positive function. There's a good reason for that. If your velocity function is sometimes positive and sometimes negative, then the area bounded by that function is different from the distance traveled. And if you tried to calculate the distance traveled using the scheme I'm describing here, you would get into some trouble. You would get something called the displacement instead of the distance. Displacement is how far you end up from where you start, which is not necessarily the same as the distance traveled. If I walk from my house to the grocery store and then back to my house, I've gone about 3 miles, but my displacement, because I end up where I started, would be 0. We'll talk more about that in section 5.2. All right, what I would like to do at this point is just calculate an example. So your book has 1 or 2 in here that aren't bad. Yeah, so if I want to estimate how far I've driven over a 30-second time interval and I take speed readings every 5 seconds, let me get this table. Let me copy this information down. I'm going to say, suppose v of t has the following table. T, v of t. And I'll write it oriented vertically the way we normally write tables for functions. 0, 17, 5, 21.
So they've just told us where the rectangles are essentially by giving us
Exactly.
points.
Yeah, they're giving you the sample points. 10, 15, 29, 20, 32, 25, 31, and 30, 28. Now, for the record, please don't ever do this. If you're driving and you get out a note card and start trying to sample your velocity at 5-second time intervals, you're gonna crash. In fact, everything from here down would be 0 because you would be smacked into a tree. Please don't do this. But if somehow you are able to log your velocity without logging your speed, or sorry, without logging your distance, which isn't how cars work, but whatever, and you got this data out, we could approximate how far you want. So let's approximate the distance traveled from t equals 0 to t equals 30. And before I do that, I'm gonna plot this thing really quick. We got to get all the way up to 30. We got 1, 2, 3, 4, 5, 6, 7 sample points. So 5, 10, 15, 20, 25, 30. And my speeds range from 17 to 20-ish. So let me start with a little over 30. Let me call this 30. Means this would be 15. So we're starting at 0,17, which is like up here. And then we have 5,21, which would be like here-ish. Doesn't have to be perfect. 10,24, a little higher. 15,29, a little higher. 20,32, still going faster. 25,31, which slowed down a little bit. And then 30,28, we're down a little further. All right, so I have some velocity curve that fits this data. This data comes from some velocity curve. But if we want to approximate how far we've gone, we could set up two kind of Riemann sums. I'll draw in the left endpoint Riemann sum. So here's my left endpoint Riemann sum. I'll just keep drawing these. So still working on drawing these. All right. So if I sum the areas of these rectangles, that will give me an approximation for the distance I traveled. This would be L1, 2, 3, 4, 5, 6. And it would be calculated as V of 0 plus V of 5 plus V of 10 plus V of 15 plus V of 20 plus V of 25. Those are all of the heights, and I'm factoring out the width. Each width is 5. All right, so this is like the sum times delta x. Here it's a t, but the sum of the V of ti times delta t. So that would be 17 plus 21 plus 24 plus 29 plus 32 plus 31, all times 5. And there's no shame in using a calculator when it comes to this stuff. Let me use Desmos. 17 plus 21 plus 24 plus 29 plus 32 plus 31. It's 154, all times 5. I'll write the 154 down. So that sum is 154. And when I multiply that by 5, I get 770. We should think a little bit about the units, right? So I haven't written the units for the velocity here. They told us that the units of time were in seconds, right? Time is in seconds. The velocity is in miles per hour. So if we want to give our distance in miles, then we need to think a little bit carefully. So let me just come back over here and annotate this. The time t is in seconds, and this is in miles per hour. So really, this is 154 miles per hour times 5 seconds. So this has units, miles over hours times seconds. And if I want to convert this into miles, right, I've already got the
Multiply
units.
5 by 60 twice.
Right, I've already got the units of miles here. I've got an hour downstairs. I need to convert these seconds into hours. So this is miles per hour times seconds. And if I want to get rid of that, how many seconds are there in an hour? There's 60 seconds in a minute and 60 minutes in an hour. I would have to divide this by 60 squared, right? Yeah. So I'll write it like this. And that will give me miles. So 60 squared. Desmos back. So we get 0.21389, we'll call it. And that's our approximation. All right, so we're going to go about 2/10 of a mile if we're going these speeds over this time. Now, one thing that's not obvious here, because this velocity function is not always increasing, nor is it always decreasing, it does a little bit of both, is whether this is an overestimate or an underestimate. We know it's not exact. And if we think about the curve that might fit this data, assuming that it is a reasonable curve, not something crazy, maybe something like this, it appears most likely that this is an underestimate, because it looks like, if I connect these dots with a somewhat reasonable looking curve, which velocity curves usually are, that we spend more time with these rectangles underneath the curve than we do above the curve. If we wanted to, we could also calculate R6, which would mean deleting this 17, keeping all of these, and then adding the 28 at the end, and then doing the same thing. And R6, I suspect, would be larger. Let's just squeeze it in here, and then I will let you guys go. So that's L6. R6 would be all of this stuff, but not this, right? So 21 plus 24 plus 29 plus 32 plus 31 plus 28, all times delta t. And if I come back here and delete the 17, add the 28, that's 165. So we get, I'll write these down, 165 miles times 5 seconds. That's miles per hour times seconds. And if we divide that by 60 squared, we get 0.229167 miles. So indeed, R6 is a little bigger. I guess I should shake the equal sign here because I did round.
Is R6 not missing a number? Shouldn't there be some other V of something in R6? Like, I don't think we've given
No.
the
So both of
information
these should
for
have
it.
6 terms, right? L6 and R6 should both have 6 terms. L6 starts at V of 0 and ends at V of 25. R6 starts at V of 5 and ends at V of 30. But they should both have 6.
Oh, okay.
1, 2, 3, 4, 5, 6. Yeah. So that's the difference. Remember, Rn, sorry, I'll write Ln over here. Ln is the sum from I equals 0 to n minus 1. I'll write it as V of Ti times delta t. And Rn is the sum from I equals 1 to n v of ti times delta t. So they have the same number of terms. It's just that the L sum starts at the far left and ends, look at the picture here, the height of this last rectangle is not determined by this point, it's determined by this point. So the L6 sum goes from the 0 up to the 25, and the R6 sum would start at 5 and end at 30. So we were correct that L6 is the smaller of the two, which means that the true value of that distance is likely somewhere between, 0.21389 and 0.229167. And yeah, that's about it. So there is this beautiful connection to physics here, where the area under the velocity curve is your distance traveled, but only if your velocity stays positive. If your velocity goes from positive to negative, i.e. if you change direction, then you're going to get something else instead. And we will talk about that something else and introduce this nice notation for the exact area and stuff like that next time when we talk about section 5.2, which is on the definite integral. Alrighty, I am going to go ahead and end our class here for today. I hope you guys have a lovely rest of your day. If you want to chat, you can come see me in office hours, send me a Canvas message or an email, all that good stuff. There will be a new homework set opening up today. I'll get that posted for you in the next few minutes. And that's it. See you guys on Wednesday.
I have questions for your graph. You
Sure.
just show the graph. From the if the left end points, you was on the could you show the graph again?
Yes, yeah, sure. Here we go. So yeah, this is the picture.
If the
for
left
L6.
hand points from the 0 and the graph is 17, right? 17 multiple 5. But if from the right end point, you are the same. Actually, I think right end point is the same. It is the same height with the left end point.
Well, let me draw
Because
the right endpoint picture here. I think this will probably clarify whatever it is that's bugging you. So I'll try to chop this up so it looks similar. 5, 10, 15, 20.
at the t is equal to 5, you have different height. One is 17, the other is 21. On the x, t is equal to 5. But if on the right end point, you still choose the same height with left end point, t is equal to 5.
So the height will be slightly different. The first rectangle in the left endpoint picture is 17. The height of that first rectangle in the right endpoint picture is larger. So here is 17, right? If we're using right endpoints, that first rectangle has height 21. Whereas here, that first rectangle has height 17. So that is kind of how the left versus right endpoints change things for this particular problem. And then you'll notice that all of these rectangles are slightly different than the rectangles we get from the left endpoint sum. So if you look at the first rectangle here, he's a little bit taller, right? The first rectangle in the left endpoint has height 17. The first rectangle in the right endpoint has height 21. And if you look at the last rectangle, you can see a difference there as well. The last rectangle here, the y value there is 31. So this last rectangle has height 31. Here, the last rectangle has height 28. So there are differences between the left and right endpoint Riemann sums.
I have a question, because for the t is equal to 5, you have two from one graph, you can see one is 17, the other is 21 on the same x, t is equal to 5. But from the left endpoint, you choose the small one, the small
Well, it's because,
one.
so the point right here, this point still has y value 17. It's just that I'm not using that point to form my rectangle because I need to use the right endpoint, because this is the picture for Rn and this is the picture for Ln. So the height of the first rectangle in Ln comes from the left endpoint, which is 17. The height of the first rectangle for Rn comes from 21 because that's the right endpoint. So this point, the 0,17 point, it doesn't influence Rn at all. That's the idea. So it's not that these are the same height. This rectangle is taller than this rectangle. Does that make sense?
Yes, thank you.
Of course. Alrighty, guys. I'm going to go ahead and sign out. Hope you have a good rest of your day, and I'll see you all on Wednesday.
I will see you on the your office hour.
Okay. All right. I'll see you there.